Good morning and welcome to physics class. And I just realized that I didn't put numbers in. Bob Jones doesn't put any numbers on, and I usually try to put them in, and I didn't do that this morning. I might put them in before you see this. If I don't, you can follow along. I'm pretty much going through it, but I wanted to emphasize. I made sure that I got the material I wanted to share with you. What I'm going to do, the way we're going to do this section of chapter 23 is I'm going to talk about it today, and then in our next class, I will go through the review page. There are five math problems that to do, and we'll do those together in our next class, okay? So this class will just be a matter of, you're going to need to get some information out of this, though, because you're going to need this information to do the review page. Okay, so reflection and mirrors. So first of all, what they call ray optics. Now, we talked about the idea in the first part of this chapter that light is a wave or a wave packet, but it also can be viewed as rays because light travels in reasonably straight lines. So you can draw light as a ray of light, like a light source, as lots of rays of light. And light will travel in reasonably straight lines. Now we're going to talk about reflection. Now the other chapter we're skipping talks about refraction, which is where you bend light waves. Reflection is where you're simply bouncing light waves changing direction. Refraction also happens when light passes through something. Reflection bounces off of something. Now, the basic principle of reflection involves a couple of important words. First word is normal, which means perpendicular. We talked about normal force earlier this year. Okay, so if you're looking at a mirror, and we're going to be looking at flat mirrors and curved mirrors, but in any of them, normal line is the perpendicular line. And if it's a curved mirror, if you drew a tangent line and then you drew a perpendicular line, that would be the normal line, okay? The angle of incidence is the angle between the light ray coming in and the normal line. Okay, the angle of incidence is the angle between the light coming in and the normal line. The angle of reflection is the angle between the reflected ray and the normal, okay? So the angle of incident is between the incoming, incident meaning incoming, I don't know if that's what it means, but that's what it is, and reflection is the outgoing ray, the angle between those rays and the normal line. So the law of reflection involves two parts. First, the incoming ray, the normal, and the reflected ray all lie on the same plane. So this is two-dimensional, okay? Same plane. This is a flat situation. And the angle of incidence equals the angle of reflection. This is really important. When it comes in, it bounces out at the exact same angle as it bounced in or came in, okay? So this actually makes life really easy. The law of reflection, God made this easy for us. When light goes in, it bounces out at the same angle. Okay? So, what happens with a plane mirror? Well, first of all, the image we see in a mirror is called a virtual image. And the reason it's called a virtual image is that, a real image, you could actually put a piece of paper up and it would project on it. Well, obviously, if you look in a plane mirror, you cannot stick a piece of paper up and see yourself on that paper. So it's not a real image, it's a virtual image. And what we see is what it looks like. It's behind the mirror. That's what it looks like. Well, obviously, it's not really behind the mirror. It's actually, the light is bouncing back to our eyes, and our eyes interpret it as being behind the mirror. So it's a virtual image. And in a plane mirror, it appears that left and right sides are reversed. And if you think about what's happening, it makes sense. Your left shoulder light goes into the mirror and bounces straight back at your left shoulder. Your right shoulder light goes in and bounces straight back at your right side. Because if you think about this, it's a plane mirror, it's a flat mirror. So if light's going straight in, it bounces straight back. Well, what that means is that your left side is directly in front of you on your left side. But normal people, if they're standing in front of you, when they look towards you, their right side is pointing at your left side. And so that's why we say it looks reversed. In many ways, it's not reversed. The left is on the left and the right is on the right. It's just that we're not used to people doing that. When people are standing in front of you, looking at you, like you look like you're looking at yourself, they are facing the opposite direction, so their right and left sides are opposite of yours. I hope that was clear. If you're using multiple plane mirrors at various angles, you can see multiple images. So for example, if you take two mirrors and put them at a 90-degree angle to each other, you get 3 images. If you take those two mirrors and put them a little closer together so they're at a 60-degree angle, then you get 5 images. If you tilt them at a 45-degree angle, then you get 7 images. And so you can actually get a formula for this. The number of images for a given angle is this formula. 360 degrees divided by theta minus 1. That's the number of images. You want to write that equation down. If you haven't written anything else down so far, you should have been. This definitely write down. N equals 360 degrees divided by theta minus 1. This equation helps you find the number of images for 2 plane mirrors at a particular angle to each other.
So what about curved mirrors? And the curved mirrors come in 2 forms. Concave mirrors, which make a cave, so the light is bouncing off the inside of the cave, and convex mirrors, which bulge out, and so the light bounces off the outside of the mirror, kind of. Now, they're going to talk about this quite a bit. Spherical concave mirrors produce spherical aberration, which is not an issue with parabolic mirrors. And we'll say more about that later. Spherical mirrors, however, the math is easier, so that's what we're going to do. We did do parabolic focus in advanced math, so you've all done that. But you can just be thankful we're not doing that for this particular activity. So the principal focus, or the focal point, and the distance from the focal point to the mirror is called the focal length. Okay, so that's important. The focus of the mirror is highly important for everything we're going to talk about. The radius of the mirror is important for spherical concave mirrors, which is what we're going to be looking at. So for a spherical concave mirror, we're caring about the radius of the mirror as well. So if you imagine the mirror as a concave mirror, but if you continue to make a complete circle out of it, you would get a circle of radius r, okay? And the center of the spherical mirror is the center of the spherical surface. Therefore, the line through F, the focus, and C, the center, intersects the mirror at its vertex, called the principal or optical axis. Most of this is just kind of geographic terms, geographic vocabulary. We'll see this when we start drawing pictures, okay? But so what you've got then is, well, let me get to the pictures as soon as I can. A spherical concave mirror has a focus halfway between the vertex and the center of the circle, okay? The center of the circle, or center of the sphere, and then the vertex, which is what the edge of the sphere, halfway between those two is the focal point. So we have this equation. Another equation you need to write down. The focus point, the focal length, is half the radius. You do need to know that. I'm not going to use that a lot, but we will use it. Okay, I'm going to apologize for this diagram. It has a lot of really cool stuff on it, and I wish it would have given it to me in a way that I could have built it up rather than having it all here at once, because it gets a little confusing. But let's start at the top. So the radius of this sphere goes from the edge of the mirror, the sphere, into the center of that imaginary sphere that the mirror would create. The focal length is half of that, so you can kind of see that relationship. In the middle, you have this line that goes from called the optical axis. If you see that, goes from the vertex, which is on the mirror itself, through the focal point and through the center. Okay, and they're going to illustrate 3 different kinds of rays here that are important to us. So imagine light rays coming in, what they call parallel. These are light rays coming in a straight line, parallel to the optical axis. And you've got 3 of them, and they're labeled 1. Oh, you got 4 of them actually. They're labeled 1. Got 2 near the top, 1 in the center, and 1 at the bottom. And what you notice about all of these, they're coming in parallel to the optical axis, bounce off the mirror, and go through the focal point. You see that? They go through the focal point. So all 3 of these lines go straight into the mirror and then bounce through the focal point. And if you look at where they hit the mirror, you'll see that their angle of incidence equals their angle of reflection. That's our basic rule. Angle of incidence equals angle of reflection. So if you look at those 2 angles, and they have a little dotted line there to show you the normal line. So it's the inside angle that we're looking at. Okay, the angle inside the green angle
where the dotted lines are. We're looking at the angle incident and the angle reflection. They're the same. And the two lines up above, they bounce in, they bounce out, go through the focal point. The line down below, same thing. The line down the middle does also come straight in and bounces straight back out through the focal point. Number 2 is illustrating lines that come in through the focal point will bounce out parallel. So if you look at the yellow line there, it comes down through the focal point, hits the mirror, and when it comes out of the mirror, it's coming out straight. Again, if you look at the bounce point, it does have an angle of incident and angle of reflection. They're the same. There's a number 2 line that goes straight through the focal point also along the optical axis. That's really not that interesting, to be honest with you, but it's there. Okay, so here's the key. Lines coming in parallel go through the focus. Lines that go through the focus come out parallel. Okay? And then the third thing that they show you there with the pink line as number 3 is that any line that goes through the center will bounce back through the center. And we don't use that one much. That rule doesn't get used much, but it is there. If the line goes through the center of the sphere, it will bounce off the mirror and come right back out. That's because it's going to hit right along the normal line. It's going through the center of the sphere. It's going to hit normal line. So the angle of incidence is 0, so the angle of reflection is 0, so it comes straight back through. Okay, so that kind of shows you what do we mean by focal point, center, vertex, etc. Now, they give you some definitions. The object distance is the distance of the object from the mirror. The image distance is the distance of the image from the mirror. They just chose a weird font for that I. But anyway, okay, so these are kind of straightforward, kind of obvious, but you have to use these terms. So object distance, d sub O, is the distance the object is from the mirror. Image distance, or d sub I, is the distance the image is from the mirror. So, there are 6 possible cases with the object located on the optical axis. Now, they give you another definition. We're going to talk about all 6 cases in just a moment. A real image is one which can be focused on a screen. I said that earlier, and that's always going to be in front of the mirror. So if it bounces off the mirror, you're not going to look in the mirror and see it. You're going to hold a piece of paper out in front of the mirror and actually see the image projected on that paper. Okay, that's a real image. If it's a virtual image, you're going to see it in the mirror, look like it's behind the mirror. So now let's look at examples of how the reflection works in a concave mirror. And then we're going to talk about the math afterwards. Okay, the equations are later. Right now we're going to draw pictures. Okay, and they start with what they call case 2. This is where the object is beyond the radius of is farther away from the mirror than the radius, so it's behind the center. Now, look at what's happening here. This is actually just drawing arrows. Makes sense, but you have to be careful, okay? So what we do is we follow 2 rays from the top of the image, and we use ones for these images, like a concrete 3-dimensional 1, and we just take the top of the 1, and we draw rays, and that tells us where the top of the image is going to be, and then we draw the image down from the top to the center line. So we take this 1. Now the first ray, going from number 1, green ray, goes in parallel. It's going straight in from the 1 to the mirror, and that means it bounces through the focus point. And so we draw it straight in, and then we draw it through the focus point. You need to draw fairly straight lines for these to work. Number 2 is going through the focus point. So it leaves number 1, goes straight through the focus point, but that means that it's going to bounce out parallel to the optic line there. Where those 2 lines cross is the top of the 1. Now please notice that it is upside down, it is in front of the mirror, which makes it real, and it is smaller than the original. So if you are standing behind the radius of the outside the radius of the mirror, your image is not going to be something you can see in the mirror. It'll be dangling down in space. You need to have some sort of elevated spot to make this work. And you'll be upside down. You'll be about half your normal height in this particular image. And you will could be projected on a screen. You actually wouldn't see that image, I don't think. You'd have to put a screen there to project it onto the screen. Okay? That's what they call case 2, where you're outside the center. Then they skip to what they call case 4, where the item is between the focal point and the center or the radius. Okay, so this is this image, and you see there it is between the focal point and the center. Again, we draw ray number 1 goes parallel to the optic line and bounces through the focus. Line 2 goes through the focus and bounces back parallel. Where they cross is the point of the 1, and you see that this is an upside down 1. You see it as a larger than the original, and it is an image. So if you had a screen there, it would project onto the screen. It's in front of the mirror. Okay? Are you with me so far? Yeah, I hope so. If not, you're out of, if you're not, just go back and re-listen to it. Look in your book also. The book does the same thing I'm doing. Case 3 is where it's sitting on the radius. If it's sitting on the radius or on the center, again, this is the same in every single one, just the lines go different places. Draw a straight line from the top of the 1. This is line number 1, green line. Parallel in, bounces through the focus. Number 2 goes through the focus, bounces out parallel. Where they cross, what we get then is a perfectly upside down image, a real image again, exactly the same height as the original, and the same distance from the vertex. It just flips it upside down. So if you were standing on, say, some sort of a platform, like a glass platform, let's say, and you were standing in front of a spherical concave mirror, and you were standing right on the center of that radius, you could look down and they could put a screen there, and you would be sticking, your image would be straight down, feet to feet, and head down. All right, case 1, this is where the 1 is an infinite distance from the mirror. And you'll notice that line 1 goes parallel and hits the mirror and bounces back. Line 2 is coming in from a really, really long distance, but it technically goes through the focal point parallel also and bounces back through the focal point, which means that you end up with effectively no image at all. It's a pinprick at the focus. And the problem is that both lines are basically coming in parallel. One is coming in parallel at the height of the 1, and one's coming in parallel along the focal point. And so they both bounce back through the focal point, and they're just together. There's just no image there. The 5th case is when the object is sitting on the focal point. And what happens here is that the two lines never meet. You'll notice the green line number 1 goes straight to the mirror and then bounces off through the focal point at an angle, whereas the yellow number 2 goes straight through the focal point and never gets to the mirror. And so these two lines never meet each other, so there is no image at all. And then case number 6, and this is where the image is between the mirror and the focal point. Now this one gets a little weird, but look at how this works. The green one, the green arrow, number 1, goes straight into the mirror and then bounces out through the focal point. And it just goes out through the focal point. You can see that. Line number 2, now it doesn't actually go through the focal point, because if it did that, it wouldn't go to the mirror. So what it does is you follow a line from the focal point through the top of the 1 and then to the mirror. If you follow, you see the dotted line and then the yellow line, and it hits the mirror and it goes straight out. So it's not going, technically it's not coming from the focal point, but it is. It's coming at the angle it would come at if it were coming through the focal point and through the top of the 1. Now they add line 3 because this is weird, and this is going through the center line. It goes parallel. It's the line that would go straight through the center and through the top of the 1. So they give us 3 lines on this one instead of only 2. Now, all 3 lines coming out to your eye or coming back towards you do not meet together. Therefore, they don't form an actual image. What your eye does is it assumes that these 3 lines, 1, 2, and 3, are coming from an object. And so it projects backwards and says, oh, that object must be in front of the mirror, behind the mirror, at that point where those 3 lines would converge if they went back. It's like your eye says, here are the lines coming at me, and it projects backwards. Where must they have come from? And it ignores the mirror and puts the image behind the mirror. So this is a virtual image. You actually would see this. If you're looking in the mirror, you would say, oh, in the mirror, I see me taller. Maybe you'll see that that the image is actually taller than the original. So you say, oh, I see me and I'm taller, but it's a virtual image, okay? It's not a real image. but your eye interprets it as an image. Okay, so it's kind of bizarre, but that's what happens with a plane mirror all the time. Okay, so that's the drawing part of it. Okay, we're going to do some more drawing when we do the review page. Now for numbers, okay? Equations. First one is the mirror equation. You need this mirror equation. This is another thing you need to write down. If you're not writing anything else down, you do need this equation because you'll never make it through the review page without this equation. 1 over DO plus 1 over DI equals 1 over F. And I will just mention, we've got this reciprocal equation. It's kind of like parallel resistors from the previous chapter. And one of you, I don't remember who it was on the test, when you got to the end of this, you had a 1 over F equals something, and then you just wrote that down as the answer for F. Okay, it wasn't F, it was 1 over R at that point. If it's 1 over R equals a number, R doesn't equal that number. You have to do the reciprocal. So we're going to be dealing with reciprocals and fractions in these, okay? And if the distance is behind a mirror, then it's a negative number. Okay, cool point. If it's a negative distance, that means it's behind the mirror. It's a virtual image behind the mirror. Now, magnification has to do with how much does it go up or down? How tall is it? And the equation that we use is HI over HO equals the negative of DI over DO. So the ratio is determined by the ratio of the distances, but the negative sign means that actually has to do with flipping it. That's why you'll notice all of the images we had were upside down, so you're going to get a negative height because they're pointing down, except for the virtual image, because there you've got a negative distance. Because you have a negative distance, it makes it a positive height, and so it's actually goes up the right direction. And then magnification is just that ratio, the absolute value of the ratio between the image height and the image object. Or the image height and the object height, excuse me, not listening to myself very carefully. Image height and object height. Okay, so those three equations, you do need those three equations, okay? You need, this relationship of heights to distances, and this, you need the magnifications, okay? Okay, just a couple of comments about spherical versus parabolic mirrors. In a concave spherical mirrors, not all incoming rays are reflected, so they actually pass through the focal point. We assume that. Reality is, it doesn't quite happen. They go real close to the focal point, but not quite, and so you end up with a little blurring. And the flatter the mirror, the larger the radius, the better you get. But you do have this problem. A parabolic mirror, that doesn't happen. A parabolic mirror, every single ray goes through the focus. And if you remember when we did parabolic equations in advanced math, we learned about the focus. And we learned how to find the focus and the axis of, what was that thing called? Y equals something. I can't remember what they called that now. Anyway, we found those. But we're not going to deal with those, any math with those or any diagrams with those. Parabolic mirrors are going to be very similar to spherical mirrors. Math is just a little different. All right, that covers the information. What we'll do on the review page then is to practice actually doing some of these, okay? All right, well, have a good day, and we'll talk again.
Well, good morning and welcome again to physics class. And we're doing a review page here for chapter 23. This is the math part of this. We talked in our yesterday's video. We talked about mirrors, and we just want to do some math with them now. And so the first one is very much plug and chug, fairly straightforward. The other ones are plug and chug, but they're not quite so straightforward. So this is on your review, section 3, which is the math section, point 1. I think the formatting is a little messed up on your review page. Calculate the number of images produced by two plane mirrors at an angle of 34 degrees. Now, we had an equation that we were given. The number of reflections is 360 degrees divided by the angle minus 1. So you plug it in, 360 divided by 34 minus 1 gives you 10.58 minus 1, and I rounded down because you can't have part of an image, and you end up with 9 images, okay? So 9 images is our total answer for that one. So you put in the angle, get the fraction, subtract 1, and then you get the
the total number of images. And again, I rounded down because we can't have a fraction of an image. All right, now the other three questions here, 2, 3, and 4, are dealing with objects and images. And so let's look at the first one. A 3-meter object, okay, so that's the height of the object, is sitting 230 centimeters from a concave mirror that has a focal length of 250 centimeters. Where is the image? Now, I had this doing this math-wise and then doing the actual like pictures, so we'll do it that way. So where is the image? It's the first question. And we have an equation for that, okay? 1 over the distance of the object plus 1 over the distance of the image equals 1 over the focal length. And in this case, we have the distance of the object, 230. We have the focal length, 250, and we're trying to find the distance of the image. So we have 1 over 230 plus 1 over di equals 1 over 250. Simple algebra gets us 1 over 250 minus 1 over 230. I didn't even try to do this one in my head. I just punched this into a calculator. I know. I try to encourage you not to do that, but in this case, I did because that was a weird fraction. Actually, I did go back and do this a little bit slower because I wasn't happy with the answer, but this is the answer. Okay, so it's negative 0.00034. You got it in scientific notation on your calculator. Hopefully, I did do this right. I'm pretty sure I did. Again, then we take the reciprocal of that. Now, this was important because when you guys did this on resistors, parallel resistors, a couple of you forgot to do this last step. So that's 1 over di. So di is going to be negative 2,875 centimeters. What that means is the image is 28 meters behind the mirror. Okay, so this is going to be way out in the mirror. You're looking in the mirror and you're going to see this way out, 28 meters out in the mirror, okay? So it's sitting a little over 2 meters in front of the mirror, but it's almost 29 meters behind the mirror that you're looking at. This is a virtual image, okay? This is a virtual image because it's a negative distance. Okay, same question, except they ask, what is the height of the image, and is it erect or inverted? Now, this is the equation that we were given. The height of the image divided by the height of the object is the negative of the distance of the image over the distance of the object. So we have the height of the image divided by 3.0. That's the original object's height. And then we have the negative sign from the equation, a negative 2875. That's the distance of the image, and 230, which is the distance of the object. And again, some basic algebra, multiplying both sides by 3, going through, we get 37.5 meters erect. So this is a vertical image. It goes up because it is a virtual image. Virtual images in a concave mirror, the virtual images are always erect. They go the same direction as the original object. And this is very large, okay, quite a bit larger than the original, which in fact is the next question. What is the magnification? And all the magnification is the ratio of the image to the object, okay? How big is the image compared to the object? And so 37.5 divided by 3 gives you 12.5. So it is going to be 12 and a half times taller than the original object. So you've got a 3-meter object, which is, a good yard. Comes up about to your waist, but you're going to be looking down there and it's going to be 12 and a half times that, okay? And then the last thing they ask you to do, now this is at the bottom of it. I said draw the pictures. I went and drew the picture here because I wanted you to see it. And I found out that I made this really difficult because it's way off screen. And so I really couldn't quite do it. But it did illustrate the point. And maybe not really well, but I tried. Part of the reason this was difficult is because I made it kind of too far away. So what we have here then is the first line, the blue line, goes parallel to the axis from the top of the 1 to the mirror and then bounces through the focal point. Okay, so follow that. The blue line goes from the 1 to the mirror and then bounces back through the focal point. Well, because it's not actually going to meet behind the mirror, in front of the mirror, it's going to meet behind the mirror, we extend it backwards. Our eye instinctively extends it backwards. The second one has to go through the focal point. Well, it can't actually go through the focal point and run into the mirror. So instead, we draw a line from the focal point past the top of the 1 to the mirror. So it's a line that would pass through the focal point. And you'll notice my lines aren't perfect. It's really hard to do this on the computer perfectly. If you're doing it with pen and paper, you're going to have troubles getting it perfect as well. It hits the edge of the mirror, which I had to kind of fake where the mirror is going to be because this one was so off. And then it bounces straight back, and you see it going off the screen to the right. Again, our eye brings it back, and you'll see that those 2 points are coming together somewhere off the left of the screen. I drew the really big one there, but it should be off the screen a little farther. I apologize. This drawing isn't the greatest drawing. If I'd realized it before I sent it home to you, I would have changed some of the numbers, but that's the way life goes sometimes. Now, one last thing to mention. This is in front of the focus, okay? And when you have an object in front of the focus with a concave mirror, you get an erect virtual image, very large, okay? All right, this is the new one. This object is sitting at 300 centimeters from the concave mirror with a focal length of 250 centimeters. And so there's our equation. Where is the image? Okay, so we plug in our numbers. Again, 1 over 300, that's the object's distance, plus 1 over di, the image distance that we're trying to find, and the focal length 1 over 250. Once again, we do the algebra, we punch it into our calculator, we take the reciprocal. Don't forget to take the reciprocal, and you find the answer is 1,500 centimeters. This one is positive. That means this is a real image. It's 1,500 centimeters, which is a long ways from the mirror, but it is a real image. So if you put a piece of paper up there, you would actually project the number 1 or whatever your object is right onto the paper. The next question is, what's the height? And is it erect or inverted? So again, we punch the numbers in, the height of the image, which is what we're looking for, divided by the height of the object, which they tell us is 6 meters. So that's about 2 yards. Or no, 6 meters, sorry. Well, I said 3 meters last time. I said, 3 meters. The last one would have been about 9 feet tall. This one's about 18 feet tall, so fairly good size. Maybe actually a little more than that, more like 20 feet tall. And then we have the opposite of the distance of the image, which we just found to be 1,500 in the previous slide, divided by 230. And we do some algebra with that, punch it through the calculator, and you get negative 39.1 meters inverted. So this is a very large image, and it's upside down. So it's going to be projected down. So if you were standing on the floor, it actually would be projected into the floor, and you wouldn't be able to see it. You have to have some sort of this has to be up in the air so that you can actually see it. Magnification then, there's our equation for magnification, there's our question for it. What is the magnification? And the magnification is the height of the image divided by the height of the object. 39.1 divided by 3, so we got about 13. So 13, the image will be 13 times as large as the original object. And if you look at my diagram here, so we've got the line going from the top of the 1 into the mirror. The mirror, it bounces off the mirror through the focal point and goes out. The second line starts at the top of the 1, goes to the focal point, hits the mirror, and bounces back. And again, I had to kind of fake where it does that. And we end up with an image way out there and very large. Again, it's not perfect, and I apologize. Again, if I realized where the numbers were going, I would have fixed the numbers before I sent home the review, but I didn't. So that's life. So that's what it looks like. And you kind of can see how this works, though. This is between the focal point and the center, and so you end up with a very large real object inverted. And the last one, we have a 0.400 meter object, and you'll notice on your review page I forgot the unit. So there's the unit for you. It's sitting 100 centimeters from a concave mirror. The image is 65 centimeters from the mirror. What's the focal length? This changed the question, but it doesn't change the equation. Same equation. 1/100th, that's 1 over the object's distance, plus 1/65th, 1 over the image distance, gives you 1 over the focal point. So we just punch that in our calculator. We don't have to do any algebra this time. And 1 over the focal point is a 0.0254, which means the focal point's at 39.4 centimeters. Okay? Again, it's mostly plug and chug. It's just not necessarily simple plug and chug. And you have to follow what's happening. That's helps with the drawing helps with that. A 0.4, that same object, what is the height of the image? And of course, we have that equation for height.
Height of the image over height of the object equals the negative of the distance of the image over the distance of the object, which we have right there, punching in all of the numbers, doing some algebra, and you get negative 0.260 meters inverted. So this is actually smaller, you'll notice, and it is still upside down. Okay? The real objects are always upside down. The virtual ones are always upside right, just for the warning. Magnification, again, height of the image divided by the height of the object makes it just the ratio of the two. So the magnification here is 0.65. It's 65% as tall as the original image. And again, I drew the picture. This one actually worked out better, but it illustrates just that I'm not perfect doing this. So the blue line there goes straight from the top of the one into the mirror and then bounces through the focal point. The second one goes from the top of the image, or top of the object through the focal point and then straight out parallel. And where they cross gives you the image. And again, it's not perfect, but it's close to the right place. And it does give you a little bit of the object clearly is smaller. That's the way they really should look. That one looks pretty good. Okay, I don't know if this helped you or not. If we were doing this in class, we'd probably do a lot more examples, but or we could talk more about it. But I hope that this gets it for you. So go ahead and text me. Tell me the light dawned. Hopefully the light did dawn on you as it bounced off the mirror. And so just let me know that. And if you have questions, let me know those also. You can either do that on Discord. We can have kind of a group discussion if we need to. Or you can private text me. Either way works. All right. Well, tomorrow then we are going to do a summary, kind of a review page on the 2 chapters. And we'll be done with this.